Observe a standard simulation of the universe: cold, dark matter collapsing under gravity. What you are looking at here operates on a different set of rules entirely. This is a uniform, high-coherence phase field, spontaneously fracturing into a complex, interconnected web of nodes and voids. The standard cosmological model asserts that the observable universe's structure forms through gravitational instability. Matter pools into dark matter halos, creating the filamentary web we see in deep space surveys. The information manifold model approaches this from an information-theoretic starting point. It tests a specific hypothesis. The macroscopic topology of the universe emerges organically from information processing axioms, requiring no gravitational primitives to take shape. This framework does not attempt to derive the tensorial Einstein field equations. Instead, it models reality as a dissipative reaction-diffusion-projection system, treating informational configurations as points on a differentiable manifold. When this system is subjected to a co-moving, expanding metric, it generates three-dimensional topological signatures. Those signatures match the morphological properties observed in large-scale cosmic structure surveys. If purely informational dynamics can replicate the exact geometry of the cosmic web, the architecture of our universe may be an emergent property of data processing acting on a massive scale. The information manifold model relies on two primary field equations. They dictate how a continuous coherence field, denoted as psi, evolves over time. The baseline mechanics involve a physical dilution. Spatial diffusion of coherence spreads information outward, but it is constantly suppressed by Hubble friction, which weakens the field's intensity as the metric expands. To counter that expansion, the model employs a curvature operator. Sourced by entropy gradients, this operator acts as an attractive force. It pulls coherence density toward high entropy peaks, functioning as the informational analog of matter condensing into a gravitational potential well. The system is then subjected to a nonlinear projection operator. This is the primary driver of decoherence. When projection strikes these regions, it forces a dissipation event, instantly collapsing the coherence and leaving behind localized entropy. To prevent the system from settling into static equilibrium, continuous zero-point energy fluctuations inject a baseline noise. This continuous variation provides the raw material for the field equations to process. The entire process of structure formation reduces to a mathematical competition. Curvature-driven coherence growth builds density, while projection-driven dissipation actively removes it. To observe the macroscopic results of this competition, we translate the continuous equations into discrete parameters. A 32-cubed voxel lattice evolved over 250 specific time steps. This chart tracks field amplitude and entropy. The blue line measures mean coherence, decaying to 0.83 via Hubble friction. The red line tracks peak coherence. Curvature coupling locks density into spatial coordinates, stabilizing high-amplitude packets. On the right, entropy accumulates at a steady linear rate. This decay is not random. As the simulation progresses, the effective spectral dApp drifts toward a critical band. When it hits that band, projection events multiply rapidly, tearing apart the global phase and triggering widespread decoherence. The time evolution forces a mathematically inevitable percolation transition. The uniform starting state cannot survive the projection dynamics. It is mandated to fracture into isolated coherence packets. By simulation step 250, the environment reaches freeze-out. The topological structure permanently sets into a spatially inhomogeneous distribution. These orthogonal strices map the field at freeze-out. The top row isolates coherence amplitude, with bright spots identifying localized density packets surviving decay. The bottom row measures accumulated entropy, revealing a precise inverse geometric relationship. Wherever coherence collapsed, deep blue void regions took its place. The space has bifurcated into a binary system. Surviving coherent structures are entirely surrounded by an expanding thermodynamic exhaust. Because we are looking at three orthogonal cross-sections, we know this complementary structure is isotropic. It is a genuine three-dimensional network, not an illusion created by a two-dimensional slice. The initial uniform informational field has stratified. The resulting physical topology provides a structural mirror to galactic clusters, separated by expansive cosmic voids. Visual similarity is not mathematical proof. To quantify the morphology of this density field, we apply Minkowski functionals. the framework used by astrophysicists to analyze observable cosmic geometry. We apply a thresholding parameter to the coherence field, isolating values strictly at 105% of the mean. This creates a hard boundary delineating structure from void. This image highlights the resulting boundary contours in cyan. By calculating the volume fraction of the manifold occupied by this coherent structure, the simulation returns a value of exactly 29.97%. In the observable universe, roughly 5% of the volume is occupied by galaxies and halos, while 70 to 80% is dominated by void. The information manifold model produces this approximate 30-70 split organically, without parameter tuning. The topology holds up under deeper analysis. Measuring the specific enclosed cavities and connecting tunnels formed by those boundaries yields an Euler characteristic of -1602. In Minkowski analysis, a positive Euler characteristic describes a universe of isolated, disconnected clusters. A deeply negative value proves the geometry is cavernous, interconnected, and highly percolating. The metrics confirm the outcome. Subjecting pure information to projection dynamics spontaneously generates the spongy, filamentary topology of the physical cosmic web. The geometry maps to astrophysical reality. The dense coherence packets function as informational analogs to dark matter halos, and the entropy-saturated zones behave as expanding voids. This mapping offers a structural perspective on the cosmological constant problem. Standard quantum field theory currently calculates a vacuum energy density 120 orders of magnitude larger than what we actually observe in space. Under the IMM framework, that enormous baseline energy corresponds to the unprojected manifold, the raw field before the system processes it. The projection operator acts as a cosmic phase eraser. It localizes a fraction of that raw energy into surviving structural packets and destroys the coherence of the rest, filling the vast majority of the manifold with decohered entropy. In this model, the expansive pressure driving the universe apart is not the energy of the quantum vacuum itself. It is the residual entropy pressure of these decohered voids, pushing against coherent structures. This identifies a mechanism by which the massive energy of the bare vacuum could be localized or erased. It redefines observable space as the thermodynamic exhaust of the projection operator. The model implies a scaling of these principles across 12 orders of magnitude. The field equations that construct this galactic web are structurally isomorphic to the gradient flow equations the IMM uses to model cognitive receiver architecture. Both systems rely on a single stability potential. Whether predicting how a human brain interprets a signal or how a universe distributes galaxies, the math models the competition between coherence-building integration and decoherence-driven projection. This topographical plot maps the cognitive receiver stability landscape. The peaks, valleys, and saddle points that dictate how an agent processes signals mirror the coherence landscape that dictates where cosmic matter forms. Cognitive interpretation regimes and macroscopic cosmic voids are different scale expressions of the same mathematical attractor dynamics. Large-scale reality operates on the same constraints as local observation. The resulting cosmic architecture stands as a scale-invariant expression of universal information processing.